Good afternoon, folks. It's Gord Cook. We'll start here in just a few minutes. Let a few more sign in. Already some good numbers. Stacy?
Yeah, we're doing pretty good, Gord. Yeah, I think we're pretty good to start.
Great. Well, welcome, folks, to part 6 of the Critical Canadian Home Building Science webinar series. This one's on HVAC and ventilation. You guys will know we've been very pleased at Building Knowledge Canada. We've been very pleased to work with Enbridge Gas Distribution on this seminar series, and we just really enjoy the experience and really appreciate folks signing in on a regular basis. Would encourage you to participate as much as possible in the Q&A in the chat. I have with me a partner at Construction Instruction down in Denver, Justin Wilson. I'll give him a chance to introduce himself in just a second, but I'll just move over here, and Stacy, if you wouldn't mind going through the housekeeping rules.
Yep, so we just want everyone to know that when they have the questions for either yourself or Justin, that they do so in the little box down below. That's called Q&A. And that's where all the Q&A part gets documented, and it's easier for us to answer that because it pops up easier for our speakers. And the chat is where we would like you, like Zoran's already done, saying hi everyone. And if there's, when we do the polls, if there's a part that we've missed or an occupation that we've missed, then put that in the chat box. Otherwise, let's keep every type of question. The comments that they make about your presentation, that's okay to put in the chat when they want to just talk about their own experience. So that's good over there. The Survey Monkey that goes out after our presentation, it is a feedback form that we love to have so we can keep delivering amazing content for everyone and their needs in the building world. And so that survey goes out immediately after our presentation is done. And as always, we send out a resource email to everyone that has registered. And if you want to forward that on to your team, you're more than welcome to, and that will have today's recording as well.
Thank you. And so we'll do just our little bit of housekeeping, and then Justin and I will be chatting till just after 2 o'clock, and we have left ample time for questions in this particular seminar. In fact, that's why I really wanted Justin be here. His technical knowledge of HVAC systems, what you're seeing, he's actually sitting in a little demonstration house. Justin, how many different heating cooling systems do you have there at the CI Live Experience Center?
Well, so in a small house back here, so it's good to see everybody, first of all, Gord, so thanks for having me this afternoon. Morning here still. We are in a small 500 square foot house in the rear of our lab, and we actively test different systems here. We've got today, and we're about to change out a system. Primary system, we have a 2-stage gas-driven furnace with a 2-ton, 2-stage 18-seer air conditioner on it, and that runs underneath me here in the floor system, and that has multiple zones and also ways to trick the zones on and off to induce different pressures or look at different flows through different ducts if we're looking at velocities and so forth. Second system is a variable refrigerant flow heat pump system in a traditional upright vertical package. That is, and it'll seem odd to some of you, I think, servicing an attic area above me, which really represents a big portion of the United States. For those of you that have looked around here, is why are the registers in the ceiling? You ask yourself. Well, unfortunately, that means a slab on grade construction or sometimes crawl spaces. We're feeding stuff up into an unconditioned attic. So we've got insulated flex duct that's exposed and so forth. So that is system 2. And system 3, up here, we've got a wall mount VRF heat pump unit, a Mitsubishi Hyperheat system. In addition to, our classroom has a 4-zone hyperheat heat pump system, and our lab back here has a big 5-ton non-hyperheat. We use it mostly for cooling, but a long-range throw, a big commercial type wall mount heads that have about 50 feet of throw on them. So, and then Gord, we have 1, 2, 3, 4, 5. 3 of them are active ERVs back here to test today. I'm not testing them in the session, but we're working on them. And then we've got one big one on top of the classroom. So we're loaded full of different stuff here when we talk about the HVAC stuff.
Attaboy. So that's the CI Live Experience Center down in Denver. If you guys, we welcome you down there. Look online at constructionstruction.com. We have an HVAC session actually coming up, Justin, in September. 2 days designed specifically for builders to use more about HVAC systems. And again, selfishly, that's why I wanted Justin to come on today, just to say, if this 90 minutes isn't enough for you and you want to know more, get down to the CI Live Center. So thanks, Justin.
Yeah. And there's an exchange rate thing, Gord, but I'll throw it out there. So I will say whatever our listed price is for a session, you can pay it in Canadian dollars if that's a deal for anybody. What do you think?
I love that deal. Thank you. The value of that goes up and down, of course. So yeah, thank you very much for that.
Today, I think it's pretty good value.
Yeah, exactly.
Yeah.
And it's always useful, Stacy, if you wouldn't mind, just if we could run the polls just to see where folks are from and so on. Folks will know how to answer. We often, Justin, have a few folks from the U.S. Some of them you'll recognize the names.
That's great. That's great.
They often say hello. Here's the results. So most of them from here in the province of Ontario. Don't see, there's a few there from the U.S. Thank you for that, folks. Some from, so kind of across the country, a little bit. Even somebody from Quebec. Thanks very much for signing in from Quebec. Really appreciate that. Thank you. And then I think the second poll is, who are we talking to? And there's an actual one there for an HVAC contractor, but.
We're getting a lot of others, so if they want to put it in the chat, that would be great.
A lot of others. That's interesting. Very cool to know that. And if you wouldn't mind, if they've listed those, Stacy, tell us in that chat what we have there.
Good. We're seeing manufacturer, utility technical energy advisor, warranty and service specialist, residential sector council.
Nice.
And we always are honored to have the Enbridge Gas employees show up. So thanks, guys.
Yeah, thank you very much. I will say there's only a couple of HVAC contractors on the call. Hopefully we won't offend you at any point. What I will say is we need to have more HVAC contractors kind of understand these loads. We still see, confusion is the wrong word, because obviously HVAC contractors are very knowledgeable. I just think sometimes they are unfamiliar with what we're facing and the dramatic change that we're facing in new houses, and HVAC contractors are just going to have to tweak their center of knowledge, if you will, around the loads, just getting used to the loads within those high performance houses. So thank you very much for that. I think I have to click that. So I'll just remind you again, is Susan on the line with us today?
No, she is on holidays this week, so she sends her regrets. And you already have a question in your Q&A, Gord, just asking you about that HVAC course.
Fair enough. Well, we'll send a link to that. If you could send them a link to construction instruction courses, that'd be great. So I'll speak on behalf of Susan's not really. I'm probably not qualified to do that, but Susan, who's the supervisor of strategic builder relations, is from my perspective, any of you know her, knows that she's just this really good industry spokesperson, or let's call it resource for the building industry. And in fact, we find Enbridge overall to be an excellent resource. And you can imagine the challenges they're going through as we move towards low carbon economies and so on. A company that is responsive to the needs of builders for low load houses, servicing and low loads, and trying to find ways to cost effectively reduce both energy consumption and carbon emissions. So really appreciate this as one of those series that we're going to chat about today. And then Justin, you and I had chatted briefly, but here's kind of what we're going to walk through today. I'm going to ask Justin to kind of be the color commentary. I'm going to play the card that we're almost at hockey season, and you got the broadcaster, the play-by-play guy, that'll be me, and then Justin, I'll ask you for color commentary as we go along, if you wouldn't mind. But in terms of what we'll try to cover here in the next hour and a bit, a little bit of refresher on some of the new sizing realities, just to kind of tune you up as to the orders of magnitude of differences, some of the opportunities and risks in high performance houses, then some of the options, and specifically heat pumps. So we'll talk about some hot water based systems, and we do want to talk about hybrid. And then I wanted to touch back on ventilation, just some new thoughts on ventilation, things that we're now seeing. If I said it this way, ventilation is the only constant running fan in your house. That is, heating systems run in the winter and not all the time. Cooling systems run in the summer and not all the time. Ventilation systems should be running all the time, or at least whenever people are breathing. And that adds some opportunities and perhaps some challenges. And then Justin, you and I have been doing a lot lately on dehumidification, primarily in the Southeast, but I think you'd agree even on the Great Lakes that humidity in the summertime is a challenge. Maybe you could just comment. Well, first of all, give them a little bit of your background just as an introduction, and then but a little sense of what we've been seeing from a moisture control.
Yeah, so again, I'm Justin Wilson. I'm one of the partners here in the construction instruction. I am in Denver, Colorado, and my background, besides being in buildings, is pretty much my life in buildings. I did work as environment sustainability director for a large regional builder here in Denver. Originally came out of the Minneapolis area, and then about 17, almost 18 years ago, been just a building science consultant and energy rater, and sort of problem solver around the country here. But this dehumidification thing, Gord, it's happening it's most prevalent, you would think Houston, Texas. That's the first, like, it's hot and humid there. New Orleans, right? And some of those areas are Mississippi. We're also starting to see it trickle up, and it's really this, and I'll sort of set it because you're going to say this anyways, but the enclosure that we're making much better, with more insulation, better glass is one of those big key drivers here. That we're seeing the sensible loads in the buildings really drop. And that means this thermostat on the wall typically doesn't know anything about the relative humidity in the structure. And so the sensible load is now minimized in the building. And the latent load, the moisture load, or the dehumidification is rising at the same time. So if the equipment now, typical air conditioning, we're going to use this as a summer example, if it's not running, it's not removing heat from the air. And as we know, Gord, it's not removing one bit of moisture from the air. So even in areas like Nashville, or moving up along the east seaboard of the United States, or a bunch of houses recently in Minneapolis, which that climate really reminds me of where you are today, Gord. It's a little bit colder, but they run that pretty high dew point condition pretty much all the summer. And so what we're seeing is this latent load, and I think it's going to be one of our big topics today, Gord, or one that we bounce back and forth on, is rising. And so all of a sudden, this thing about dehumidification in many houses and many climate zones comes. And it's not huge in some instances, but it's sort of taking that edge off, right? There's a little overbalance.
Exactly. So that'll be one of the topics near the end of the hour, but thanks for that intro, Justin, and you guys get a sense now of Justin's experience and the kinds of questions you may want to ask him as we move through today. So I thought, just for a bit of fun, I would show, this is a 350-year-old building. It's now a high-end, I'll call it hacienda, or a hotel in the highlands of Ecuador. This is a historical place where Bolivar actually signed the Declaration of Independence. It's now something like $800 a night to be as a hotel. And we happened to be there a few years ago, and it was in the winter time, and it gets cold there, not severely cold, but down below 0 Celsius, in around I'll say 20 Fahrenheit, -5, -10. And I was kind of interested. We went for dinner, lovely dinner. We got back to the room. I'm like, oh, this is going to be interesting to see how they heat this building. I thought that, what have they done for central heating in this building? And I was a little surprised that I got to the room and I couldn't find any obvious heating system. There was a little fireplace that actually was smoking pretty badly, didn't vent very well. Thinking, what are we doing for heat over the course of the night? Because it was about, as I say, -5 Celsius. And it turns out we got upgraded to a I'll say an executive room where we actually got zoned heating. We got not one but two hot water bottles for the bed. The sum total of the heating for this room was hot water bottles in the bed. And in fact, in the middle of the night, somebody would, if you got up and you were cold, a new hot water bottle was placed outside your door so that you could go and grab it, and if you ran out of heat. So I would say we've come a little ways since then, but I thought that was kind of fun in a $700 night hotel. Hopefully people don't mind me telling a story like that, but kind of cool, I think. All right, I want to go to the basic math, and I just wanted to all of us to understand that when we talk about sizing heating cooling systems, it really is about grade 6 or grade 8 math. It's really about understanding in the top formula there how much heat is flowing through a wall, floor, or ceiling. That math says I need to know the surface area of the walls, the floor, the ceilings. I need to know the temperature difference across it. So if I know the outside temperature and the inside temperature, and I just need to know the R value of that wall, floor, ceiling. Heating contractors, heating designers, this is what they do all day long. Surface areas, temperature differences, dividing by R values. The next interesting one is the radiant flow through glass, not the conductive flow, but when a piece of glass is illuminated, how much heat it is allowing in. And here again, it's equal to the area of the glass, in this case simply glass, times something called the solar incidence, which, Justin, is actually pretty difficult to find. It's a function of the latitude, and actually the elevation. Basically, it's a characteristics of, let's say, Denver, characteristics of Toronto. It just happens to be a specific number, times what folks on this call will probably recognize is a parameter of windows called the solar heat gain coefficient of the glass. This is a function of the low E coatings of the glass. Justin, do you want to make a quick comment there?
Well, the solar incidence is really a combination of if it's direct hit of a window and indirect. And so it's a composite number. And it is really hard to find, and it's buried into the software and so forth. And that will, of course, be, latitude specific. And it also is going to be, even if a window's angled or if it's perfectly vertical. So all these things change just slightly. But it's complicated because I'll give an example, Gord, is you could have some of it bouncing off, hitting a window of the house you're talking about, bouncing off the house next door. So that's an example of indirect. It's coming from the sun, but it's hitting another window or another piece of something and then actually entering another piece of glass on the building you're trying to condition. So it becomes sort of wildly complicated, but it exists, and we can find the information on it in numerous places. And it's also, of course, variable as the sun arcs from the east to the west. So it has a whole bunch of dynamic properties to it.
And that variable or intermittent load, I'm going to remind folks, it could be even solar incidence bouncing off the lake. If somebody has lakefront property, huge implication because the angle changes pretty dramatically, and you're really tough to shade that out. Or at least you'd have to shade it out differently. And Justin, we've had a couple of builders who've experienced that. They sell houses on the lake at a premium, and they have more comfort complaints as a result of that.
Exactly.
And then the last formula that's most prevalent is the heat flow via air, and that could be, say, for ventilation or air leakage. And in this case, it's the volume of the air, cubic feet per minute, times the temperature difference, again, between outside and inside, times a physics constant of 1.1. All I wanted to get at is it's pretty simple math. Anybody could do a heat loss, heat gain, as long as they know surface areas, temperature differentials between inside and out, and R values. It's really not that difficult to do. And of course, through our software programs that do that. In Canada, we have what's called CSA F280. In the US, it's called Manual J for sizing of systems. And really the lesson to learn out of this one is if we double the insulation based on those formulas, we cut the heat flow in half. If we take 1,000 square foot attic and it's 1,000 square feet, we do it in square feet because we still work in R values and our industry still works here in Canada, not in metric, but in imperial. If it's 70 degrees out and 7 degrees in and 10 degrees out, that's a temperature difference of 60 degrees, and that's a heat flow of 2,000 BTUs. So if you're putting a 40,000 BTU furnace in a house, 2,000 of those BTUs is needed to replace the heat that's lost through that ceiling. But if you double the insulation, which we have, quite frankly, over the last 20 years, to R60, you've cut the heat flow in half. And that's the lesson for any high performance builders. If you've gone from an R15 wall to an R30 wall, you've cut the heat flow in half. Your basements went from R8 to, let's say, R12. 20 years ago, R12, a half height basement, now it's R20 full height basement. You've cut the heat flow in the basement, or at least through the basement wall, in half. That's the important thing to understand as we move through this. That means HVAC contractors, we always hope there's more of them on the call to say, hey, rethink whatever rules of thumb you were using about how big a furnace needs to be. Redo those rules of thumb because insulation levels have changed. And I want to remind you that heat loss is a function of surface area, not the square footage of the house. This house on the left, 1,200 square feet, 30 by 40, has a perimeter area of 140 lineal feet. If we take the same house, put a garage into it, but the same square footage of house, that is same 1,200 square foot house, we now have a greater perimeter. And if we have a greater perimeter, we have a higher heat loss. The reason that's important to us is because we now build more complicated houses. The juts, the jogs, the bump outs, this is what creates differences, and people go, why is the heat loss in that house so much greater or less, if you will, than another house? So just keep that in mind. It's a function of exposed surface area. Exposed surface area is what we want to get to. And all of that means, and it's really quick in this level case, all that means is, as a builder, make sure you're sharing important information. That is, make sure you're sharing the new wall and attic insulation levels, your foundation levels. Make sure that you're giving your contractors the solar heat gain coefficients. And this, as you're going to see, is the most important summer variable. Justin, we had 30 builders there last week. We asked all of them, have your HVAC contractors ever asked you for the solar heat gain coefficients? And the answer was, nope.
We got a lot of no's. What, really? They can get that? Like, well, you get it from your window suppliers, and then of course they realize that it's on their takeoff sheets. So you need to pass that information to your HVAC contractor. In fact, I'm sure they really want it.
Yes. Otherwise, they're using the defaults, and the defaults aren't necessarily appropriate for the building that you're building, or the climate zone that you're in, or the windows that you're getting. That's the biggest variable in summer. The biggest variable in winter is air leakage. And of course, your HVAC contractor is going to say, I don't know how tight your house is going to be. And you as a builder are going to go, I know how tight my house is going to be because I air test them. And if you don't, here's one of the reasons to start air tightness testing your houses. If not all of them, at least enough of them, so you can say confidently, my house is 3 air changes or 2 air changes, or passive house 0.6, net zero 1.5. And when you give that number to your contractor, that helps in terms of downsizing the mechanical systems for winter use, furnace size. So we have two things. One, the windows effectively determine the size of your air conditioner, and the air leakage effectively determines the size of your furnace or heating system. And that's where you want to get to as we move through this. And there's just a little example, Justin, you haven't seen this one before, but I took a 3,000 square foot house there on the left, built to our 2009 code before we really did much in terms of energy. We would have needed a 69,000 BTU furnace, which pretty reasonable sizing. What do you think, Justin? What would they have put in or installed in terms of a typical furnace size for that kind of house?
That kind of house I was just at the other day. I saw Robbie's on the call too from the United States. He was with me. They had an 85,000 in there, an 85,000 BTU furnace.
So a little oversized, not bad, right? Pretty good shape.
Yeah.
But take that same 3,000 square foot house, and we have many builders now doing net zero ready houses, and we're at 27,000 BTUs. And the appropriate solution for that would be, well, the smallest furnace you can really buy, or technically, or at least practically, is 40,000 BTUs. Are we okay with 40,000 BTUs? A little oversized. Justin, your thoughts at 40,000?
It's going to drive a little bit to the cooling, and I think we'll talk about some of the motor technologies and choices that you have. But it's a great option in this case. If you're going to run a typical gas furnace, I would do a variable speed furnace and 2-stage, and it's going to run, still going to cycle in the low stage, but it's a good opportunity for a 2-stage upgrade.
So take the savings out of the 80,000 to go down to 40, and I get it that the change in furnace price isn't that great from 80 down to 40, but the furnace is going to be a little smaller. What's really powerful is the ductwork's going to be smaller. Take the savings you got, invest it in either variable or at least 2-stage. But as you mentioned, here's the cooling loads. The cooling loads went from 46,000 BTUs. And I think Justin, you and I agree, a 4-ton system. No, don't really want to oversize AC, 4-ton. But now we're down to 23,000 BTUs, assuming we chose the right windows. What I think is powerful, Justin, even this is at a 0.25 solar gain. The windows still account for 50%
Look at the
of
windows.
the size. Isn't that what?
What was the window? Yeah, what's the window area? Is it pretty typical, like 15 or 20% the wall area?
13 to 15%
13.
window to wall ratio.
Wow. Yeah. So you think of, even if you make it 20, I would guarantee your numbers 55 to 58 or 60% when you add more windows. And that's, of course, what happens here. But now you're dealing with, but this is a pretty good size. That's most manufacturers of quality heating and cooling equipment have a nice pairing at a 40 or 45,000 BTU air handler furnace and a real nice 2-ton air conditioner.
So the loads are
that's what that is.
Yeah,
they're kind of in balance here, which is great to see.
Yeah. And so I just want to, and Justin made a good point. What was your window to wall ratio? One of our designers here yesterday was doing a house 52% glass, 52% window to wall ratio. And Jason was doing a heat loss heat gain on it, and he's like, wow, this is huge from a cooling load. So be mindful that as you add more glass, you're going to be adding more cooling. But also recognize, as Justin mentioned, are they facing east, west, south? Because sometimes it's not that big a deal if all the glass is facing north. That's not a big deal because it's glass that's illuminated that we're most worried about. And then, so we just go back to quickly, Justin's given you some appropriate sizing, but we always like to point out that HVAC contractors tend to oversize for the following reasons. One, they've always done it that way, which isn't a great excuse. And then second, well, they think it's hotter or colder than we think it is. We would say that's not a great excuse. But here's a legitimate one. They can't rely on customers to use shades because all cooling loads are designed with the thought in mind that homeowners will have their blinds closed. So that's an important one to understand. Is it practical with those big round top windows way up in a open to below area? What are the chances that people actually close the blinds on those houses? And here's a big one, and again, legitimately, can't rely on a builder's construction practices. Which way is the house facing, the air tightness, so on and so on. So it is important that out of this call, out of this webinar, that we have a frank meeting with our HVAC contractors and designers and say, yes, I will meet these air tightness levels. I will make sure my window manufacturer sends the right glass. And Justin, this is a big part of what we do, is trying to help builders get together with energy raters, as you say, Robbie's on the call, energy raters and HVAC contractors, everybody on the same page. Would you agree?
Absolutely. And it's everybody on your team that really can help. And, again, this comes down to that feedback loop, is the measurement part when the house is done of some measurements of air tightness that you mentioned, Gord, observation and assessments of quality insulation installation. And I would also say that there's a lot that can be done with the software. I'm sure the F280 package can do this, but we can spin the house in, 4, 8, or 16 different orientations and look at an analysis and see if that exact house, what happens when you turn the orientation of the front door and what impact that has on the overall sizing of the heating and cooling systems.
lot specific heating cooling systems. And then here's another element that we know to be true. Our standard here in Canada says 23 to 24 degrees Celsius for cooling loads, 21, 22 degrees Celsius for heating loads. We know that clients are wanting it warmer in the winter, they're wanting it cooler in the summer. So builders on this call, you need to be really clear in your documents to homeowners that says this system was designed for, set the design number, this system was designed for 23 degrees Celsius summer, 22 degrees Celsius winter. If you're going to run it something different than that, you need to be aware that it might not meet your expectations. So that's a legitimate concern in today's world. We then get these excuses about customers have big parties, they need more air conditioning. We would say there's ways to solve that with mini splits and party rooms and so on. So we wouldn't give a lot of credence to that one. And then this just in case, worst case safety factor, and we would say that is not a great excuse. So out of those items on the list, a couple legitimate, making sure that we have consistent construction practices. Two, making sure we give reasonable expectations to consumers, but otherwise we shouldn't be oversizing based on F280 results. That's really the lesson I want to talk about.
And then no matter what, Gord, so here we take all these situations here, but ultimately we're designing a house to work the best at the worst possible condition, or the most extreme, if I want to call it that condition. So that condition in the winter or the summer is probably less than 1% of the hours of either the winter or summer. So when we add all these other factors in here, we keep going above and above that to design for this one event, your party, right? Well, the system needs to be able to run, and I'll say it like this because we're still going to be hot here in Denver today, but not that hot. So it's going to be 88, but it's not going to be 97 like the design temperature. So I'm not in my 1% range, but I still want to be comfortable. So the systems are designed to run at the extreme, but we rarely see those when we really count the hours of the year.
And I'll say it another way. You're quite right. You don't want to oversize for the worst day and then add even more, right? Just design for the worst day. That's what design day heat losses and gains mean. And then, as you say, the rest of the year we still want to be in a comfort range. So that's great. I thought we would do a quick one-room example. Here's a room, bedroom 3. You'll see the house in a second. 2 exposed walls, 1 exposed ceiling, 1 window. We're showing the solar heat gain coefficient down at the bottom. I'm going to do this really quick, Justin, just as I don't want them to get hung up on the math, but just want to give a quick sense of how simple this is. And here's what an HVAC Excel spreadsheet would look like. You would take the surface areas of the ceiling, the walls, the window, you'd multiply it by the temperature difference, you'd divide it by the R value, and that would give you the BTUs for that room in winter and in summer. The one that isn't on there is the solar heat gain coefficient. So south facing, the solar incidence is 50, solar heat gain is 0.3, so I have 300 BTUs on the window. And notice that the BTUs of the glass, the 300 BTUs, is actually just the radiant gains from the glass is almost equal to the rest of the cooling loads for that room. And if we go to the west, the solar incidence goes up pretty dramatically, and now you'll get to see that one 4x5 window, the heat gain to this room on the west facing is 540 BTUs. That's the most dominant piece of that heat loss, heat gain, or at least of the heat gain. And then when we look at how many CFM does it take to heat and cool that room, we use again a very simple formula that looks at the CFM needed to provide that heat. And you'll notice magically this room needs 39 CFM to heat it and needs 39 CFM to cool it. That makes for a pretty simple duct design, right? Of just 39, 39, doesn't change summer to winter. Pretty unusual, but it just happened to work out that way. You thinking I fudged him, Justin?
No, it looks great. It looks great. It's a 4-inch run, right? There you go.
It's a 4-inch run.
4-inch run.
Yeah. But now I wanted to look at, there you see on the left-hand side the actual house layout. Top right was bedroom 3. What I want to do is go down to bedroom 2, which has same square footage but more cold surfaces because it's the room over the garage. And it has more glass to it. And let's see what happens to this room. In this case, it needs 48 CFM to heat it And we were at 4-inch duct on the last one. Now we're probably at a 5-inch duct to get to 48 CFM, but now we need 66 CFM to cool it. And this, of course, is always the challenge. And of course, bedroom number 2 is even further away from the thermostat, has different heat loss, heat gain characteristics. So it's no wonder that this room gets complaints, summer and winter. It's too hot in the winter, too hot in the summer, it's too cold in the winter. And it's because it needs more airflow, and it needs a different airflow summer to winter. And this, of course, would mean I either need to balance flows summer to winter, or I need to think about zoning. And Justin, we get these kinds of concerns all the time. Is that fair?
All the time, yeah. And this, this room, you said it's over the garage, so it's also, in most instances, the furthest run from the fan unit. So it's the wildest, longest, most constricted, roundabout duct that gets put in the building.
And that duct is often, it's buried in insulation, but it's still in unconditioned cavities, perhaps, right? Depending on how well we buried it. So
Yeah.
it's interesting that where we see these. And that's really what I want to remind us of. And here's just a little rule of thumb. 100 square feet of glass, so 10 by 10 piece of glass, is roughly 6,000 BTUs, up to half a ton of air conditioning load. So if you got 100 square feet of glass facing southwest, north is not a big issue, but east, south, or west, that's adding half a ton to your system. From this day forward, what we need to recognize is the decisions you make on windows and the size of windows has immediate impact on the size of the air conditioning, therefore the size of ductwork that goes to those rooms, and therefore the types of controls that go to those rooms. That's a simple rule of thumb: 100 square feet of glass, half a ton of air conditioning on southeast or west sides. And I always get myself into trouble giving rules of thumb, Justin. You would say, go back and do a heat loss, heat gain, but I wanted to show that. That's fair.
It's a good example though.
Right.
I like it, Gord, because at least you think like, wow, think of 100 to a half ton, 100 to a half ton, and at least our mind is saying like, okay, is that little or a lot, right?
Right. And then, of course, you could say, could I cut that by putting in different glass? Exactly. That's why you make choices on different glass. You work with your suppliers and your HVAC contractor to come up with the sweet spot. And then I just wanted to remind folks, because duct designs are a little more complicated, but I wanted to remind folks that a duct design takes that predicted heat loss, heat gain from a series of algorithms. They're not real, they're algorithms, but they're close. Then it takes algorithms that predict pressures, airflows, and losses through ducts. So it's 2 different sets of algorithms. Then it accounts for it doesn't account for duct leakage that typically are at 15 to 30% duct leakage, depending on how well you're done. And they're connected to an air handler that varies its flow and temperature rise depending on those flows and pressures. In other words, a duct design is by nature a little bit up in the air. It's a theoretical calculation. As much as I said we needed 66 CFM to cool that room, predicting exactly how much air will come out of a vent, there's a lot of calculations going there. And what we really like to show there at the CI Live Experience Center is the differences that you can get when you put in different air handlers, different ducts and zoning. Justin, you have the ability to show that.
Maybe I can do this on my floor somehow. I've got a table in here, but we've got an imprint of the duct system that's below me. Maybe you see it, Gord, I'm not sure.
I can see it. We can
but
see
basically
it.
all the runouts, there's my table I'm sitting at, and the sizes and changes, and really what's going on there is we've looked at from the furthest run and its required flow, and that's kind of what we're illustrating here, Gord, is we've looked at the furthest run, including the register, even the duct size, and then to the trunk, and relating the trunk back to all the fittings, to the air handler, to the capacity. So we're working forward and backward, typically backward in this case, where I'm looking at what my desire is. If you said it was 48 out of one of these, then I'm looking from that side and going back in from everything. So when I say a 4-inch, but a 4-inch connected to an 8x16 that transitions to an 8x20 trunk that's connected to a fitting with turning vanes in it that's connected to an air handler. As you say, there's a bit of guesswork going on here. And then when we measure, though, measuring gives us that feedback loop continually. And that's for your contractors generally are really great. After comments I hear is, they know over the years when they're good, they can say like that 6-inch duct's going to have 70 CFM in it. When it exits at the supply booth, like, all right, well, let's see what you got. And a lot of times they know.
And that is the point. These are algorithms, and they're designed for worst case, and inevitably it means all duct systems need to be commissioned. Some would call it balanced and measured, and dampers installed, because these algorithms aren't perfect, and certainly individual conditions aren't perfect. You are going to have to understand that your duct designs duct design needs to be there, and then it needs to be fine-tuned with actual commissioning and balancing is where we want to get to. So results will vary, plan on adjustments, and balancing is where we want to get to. I just show this as an example of, you said quickly when I said I needed 39 CFM, you said, oh, that's a 4-inch duct. A typical 4-inch duct on a typical system will get you between 30 and 40 CFM. You will not get 100 CFM out of a 4-inch duct. 5-inch duct will get you 50 to 60. A 6-inch duct, 90 to 110. And we can then use that to predict how much flow we need to get cooling or heating. And what we need to know is the temperature fall off the furnace, that is how much the temperature is reduced through a cooling system, is only in the range of 20 to 25 degrees Fahrenheit, whereas the temperature rise coming off a heating system is 45 to 55. And what that means is you need more air to cool a room than you do to heat a room. That is, for the same number of BTUs that I need more air for cooling. So in general, even certainly all across Canada, almost all across Canada, except maybe for northern Alberta, northern BC up in the mountains, your ductwork is determined, the size of your ductwork is determined by the size of the cooling system that's likely to go in that house. That's your learning out of this. It takes more air to cool than it does to heat. Why? Because the temperature difference coming off the furnace or air conditioner is different. That's what we need to think about. And to some extent, I don't care whether you use traditional ducts or high velocity ducts. It's really a question of CFM times temperature difference times 1.1, how many BTUs is coming out of that. We often hear the high velocity guys say, oh, you don't need as much air, because it's high velocity. No, in terms of BTUs delivered, it's a very simple formula. What's the temperature rise through the duct? What's the CFM? And this constant of 1.1. So don't be fooled and think that just because it's higher velocity that somehow it's delivering more heat. It's a matter of cubic feet per minute, not the velocity, times the temperature difference, times 1.1. Just want to keep that in mind. That said, I really think we're going to see, and Justin, you've seen a lot of this, I'll ask you to comment quickly, we're starting to see a really nice profusion of small diameter duct systems that do have a little higher velocity, therefore a little higher static pressure. That means you either need more air per vent or you need some more extra outlets. But we think there's some advantages to this, and I think you're going to be demonstrating one shortly at the Experience Center. Is that true?
Yeah, we're going to be actually installing one of these systems, and it's more of, you're going to call it a medium velocity. It's not high velocity. They're smaller, more flexible duct. Looks a lot what we've got here on your diagram, Gord. And so one of the magic things that happens here is it's utilizing some of the extra, a little bit of the extra available static in some of these newer EC air handlers and so forth. But I think the idea here is a 3-inch and 4-inch duct that you could run within a 2x4, perhaps even a 2x6 interior wall cavity very easily. And one of the other premises here would be, if I have that duct that's a little bit smaller, then I still need the flow, as you say, but I'm going to pick up a little bit of velocity, speed of the air, which is going to allow us to look at selecting locations that are, in some ways, they seem typical to you and I, but some of you are looking at atypical duct locations. If I'm speaking, I'll show one in the interior wall right behind me. So I'm facing an exterior wall, but you see this one here, which is actually facing the window wall that's behind me here. So rather than run that duct out to the window, which we've got several examples of here, we're going to jet that air and use it to mix and temper the room, and we're going to push that air at that window instead of under it or over it.
Very nice. And so we're going to see this, and the reason I kind of wanted to show that is, And when you think of how much air do you need if you doubled the wall insulation, cut the solar gain in half, cut the air leakage by 70%, you get the idea that, boy, in high performance houses, I can cut the amount of air in half that I need to a room. Remember that example, I needed 48 CFM for heating and I needed 66 CFM for cooling. But if I cut those in half, now I only need 24 and 33. So now small diameter ducts start to make a lot of sense, not because of their small diameter, but because I need lower airflow. Why wouldn't I take advantage of those opportunities is where we get to. This provides some new opportunities, of course, some new challenges in terms of, where do I place them and so on, and the look of them. So we need to think about that. The big question I always get, and I want to answer it pretty quickly, do you need return air in each room? And the short answer is go ahead, put a return air in each room. It neither helps nor hurts would be my opinion, but if you feel like you want return, that's great. But if you really wanted to know how much return air you need, what you really need to understand is I need return air to give supply air a place to go. That is, I don't want to pressurize the room. So if I close the door to the room and test the pressure with the door closed, if that pressure is less than 3 to 5 Pascal pressure, and you can say who could measure that, any mechanical contractor with a pressure gauge, and they should all have one, any energy advisor can do this for you. And if the pressure is less than 3 to 5 Pascals across the room, you typically don't need return air. An even better way to do it is to simply measure the flow. And when you open or close the door and the flow doesn't change, then return air is not going to help you in that room. That's really the case. If somebody says, oh, it's a lack of return, before you go to the trouble of adding return air, simply get a good measurement system, and a powered flow hood, for example. I'll show you one in a second. And you open the door, measure the flow. Close the door, measure the flow. And if it didn't change by more than a CFM or two, return air is not going to help. Go ahead and put in return, but it's not going to help you solve that problem. I get into trouble with HVAC contractors all the time when I say you don't need return. I would say I incorrectly said you don't need return. You do need return air. You need return air that allows the air to get back to the furnace, but whether you need one in each room is really a function of how much air goes into the room. If not much air needs to go in, not much needs to come out. So just keep that in mind as we move through this. And the science principle behind this is you can blow air 30 times farther than you can suck it. So if you're trying to improve distribution of air in a room, it's about the placement of the supply outlets, not the return air grills. High wall, low wall doesn't make a lot of difference. Justin, I don't know if you want to comment on that quickly or not, but I wanted to give you the sense it's not a high wall, low wall consideration for return. It's about where you put the supplies.
Yeah, I have to agree, Gordon. I look at the return as having the least amount of resistance on the overall return system, so that I can actually then push this back to the fan and pump that air to the room. So I don't want to have a restriction on the back of it. That's filters, undersized returns. So sometimes there are bedrooms, I'll say, like that en suite that's got a master closet, master bath, and so forth. That room's going to need a return. It's pretty good size.
Yes.
But this notion of placing a return low or high or here or there for tempering or comfort reasons has little logic from anything that we've ever measured. It'd say simply it's a pressure release, and it's a way to get air back to the conditioning system.
Thank you.
And yes, I get in arguments all the time with contractors about this. They want to put, I just saw this, and oh my goodness, for a production builder, they came in and they had a comfort problem on a whole series of houses, and they were told that they had to add return air in certain places. So they wound up dropping a laundry room ceiling to put a return through to another room. You can imagine the mess of the houses that are already occupied. And they did it like 50 times, and they called me and said, we had absolutely no difference. And I said, what did you do? And they said, oh, we dropped the ceiling and added this, 8x16 return with the grill, and had to redo part of the wall and the drywall work. And it made absolutely no difference. And I went, I wish you would have called us beforehand, because we could have told you that it was going to make absolutely no difference.
And that science actually just got put into a rewrite of HRI, Heating, Refrigeration, Air Conditioning Institute, which is the industry organization. These manuals are referenced in the National and Ontario Building Code. They just redid the Air System Design Manual that allows for, as Justin alluded to earlier, the higher static pressure allowances that we now have with new equipment. They have recognition of supplier distribution options for basements and small spaces. So when you hear somebody say you have to put registers at the floor, that may not be the case anymore. When they say you have to put a supply duct in a walk-in closet, that may not be true anymore. So remind your HVAC contractors there is a new design manual that they can use that allows for rationalization of returns, recognition of low load, high performance houses. So that's really nice. They give guidance on duct leakage and the use of flexible ducts. In other words, it's new stuff that frankly, you need to talk to your HVAC designer and say, hey, have you read, do you have a copy of the air system design, the new air system design manual? And would that help us solve some problems in walkout basements or basements in general, or small rooms or rooms over garages? Are there some new options? And the answer is yes, there's some new options. And as an example, as Justin mentioned, the traditional gas furnace now has capabilities of up to 0.8 inch of water column, external static pressure, whereas we used to design at 0.5. So that means we can use a little higher pressure. Now, some of that pressure we need because people are putting in more efficient furnace filters, but there is an opportunity now to use the added capacity, static pressure capacity of furnaces to optimize our duct system. So keep that in mind as you move through this. And
Gord, can I throw something in here real
by all
quick?
means.
So on these air handlers, there are, some of the new EC motors that have come across. There are several different variants of them, and as a builder, it's not a really big upgrade to ask. I did make a sort of divergence there at one point to say, use a variable speed with 2-stage, and there are variable speeds, modulating gas valves, so forth. But a real stock like these new from the 2016 on 2017 mandate of the more energy efficient motors, they typically have a pretty simple control board on them, and they've got only 3 or sometimes, maybe if you're lucky, 4 speed taps on them, meaning there's low, medium, high, and maybe high. So that was 5 I just gave you, but they're rarely all those. Sometimes I'm seeing only 3 on these, so they've kind of skinned them back a little bit. So some of these nicer furnaces, like up one model, for example, to that 2-stage, you really get some ability to fine tune your heating and cooling speeds that you want, even when you're doing, for example, refrigerant charges. And I'll say there's a little one here that we've got. It's a 2-stage with a variable speed. I have a Bluetooth link, and I actually can pick, and it doesn't have a low, medium, high. I can pick my heating airflow speed, CFM or liters per second. I can pick my cooling up to the targets. And it's going to optimize with my equipment to help me work within that for refrigerant charge, for example, rather than saying 1200 at this static. I can back it down a little. I can push it up in literally 1 CFM increments, because the logic board in these slightly nicer furnaces is allowing us to do that. And it can solve a lot of problems.
Thank you.
Potential, I'm going to say.
Yep. And the point I want to make out of air conditioning is we really want to make sure, and to Justin's point of monitoring airflow, is to make sure the airflow coming off the top of the coil gets below 10 degrees Celsius so that we get proper dehumidification. So managing airflows is really important to get us that dehumidification. I'll come back to that in just a little bit as well. And I just wanted to show, this was kind of a traditional fan system curve, that as the static pressure went up, the airflow actually went down. So that's those gray curves versus the duct system curves. As the airflow goes up, the system pressure goes up. So the nice part with ECM motors, I'm looking at the red dots here, EC motors in furnaces give you a constant flow. Almost regardless of what happens to your duct system, they will maintain airflow. Now they're going to draw more power, but notice that nice vertical line that says even if I put in a slightly more efficient filter, or if I put in more duct work or longer duct runs, I'm still going to get the same airflow. And what that means is, with the new residential air system design manual, it's taken that into account, and it means you can start to design at higher static pressure. It's a very useful element that we want to keep on. Then I just want to mention really quickly that in 2014 our codes changed and said we got to start sealing ductwork better, but I'm going to say even more. Our ratings are showing we're still leaking at the rate of 10 to 15% even with the code changes, and that's not acceptable for that room over the garage. Get to better sealing. Our building code says Class A seal level in class C seal level in conditioned space, which means just the transverse perpendicular joints. What I want to see is sealing all joints, and there are some proprietary systems such as AeroSeal. You blow in an aerosol, it'll seal ductwork. I'm finding this as being one of the top recommendations I find that I'm giving in warranty inspections when I have comfort complaints. I just see, because ducts are finished, walls are finished, I can't get at them, basements are finished, and I find duct sealing, I measure it, and I find the duct leakage is well over 15%, and I end up recommending a duct sealing strategy. So there is.
So Gord, well,
Go
we're
ahead.
well beyond this notion, Gord, that it doesn't matter because all the ducts are within conditioned space,
I-
so you're conditioning the whole house. That we need to seal those ducts because we need to get the air to your 39 CFM example and so forth. We need to get the air to that specific room when we need to get there. So
Exactly. That's
yeah.
the point. It's not an energy issue, it's a comfort issue. Thank you for that reminder. That's great. And so I'm not sure why that one's there. My apologies, don't need that. And then I would say we have to, as we move this session along, we have to get the heat pumps. And why? Because the best of gas furnaces are 95 to 98% efficient, but heat pumps are 300 to 400% efficient. And if we're going to meet our carbon objectives, respectful of the fact that electricity at the moment costs more, it's really hard to deny the 300 to 400% efficiency. For every dollar of energy you buy, you get $3 to $4 worth of heat. And the issue, of course, is electricity at the moment is more expensive, but even Enbridge understands this. This is why they're okay with us talking about heat pumps, because they recognize the price of natural gas is undoubtedly going to go up. Certain times of the year, people are going to say it's going to be better for me to run a heat pump that gets me 3 times the efficiency. The challenge with heat pumps has always been that in winter their efficiency tends to drop and their capacity tends to drop. So we have to make sure that we are providing the proper sizing, but I just want to go back to this coefficient of performance of 3 to 400%. You have to size the unit correctly. It has to be up off the ground. It does have cooler supply temperatures coming off the top of the air of the system, but we have to get to air source heat pumps. And the good news is there's some things that are going to help us with this. One, we have the new CSA F280 standard, which gives us more accurate heating and cooling loads. 2, we have that new residential air system design manual that gives us better sizing. 3, this guide on the left-hand side, we could send a link to this. Stacy, the new Enercan has provided this really nice sizing guide for heat pumps. And then 4, there are new equipment options that provide more consistent capacities in colder weather. And let me just show you that. Here's 2 heat pumps offered by the same manufacturer. The one on the top is sort of a traditional heat pump. You'll notice its cooling capacity, 22.5 BTUs. Heating capacity at 8 degrees Celsius outside is 26. But by the time it gets to -8, it's only 18,000 BTUs, and it's not rated at all for much colder weather. Versus basically the same company in now a in a cold climate heat pump, and notice how it maintains its heating capacity down to much lower temperatures. So that gives us a tremendous opportunity here to take advantage of these kinds of elements, kinds of new equipment. So that cold climate performance is really interesting. And it's really about finding the balance point. At what point does it make sense to run the heat pump versus, say, another type of heating? Finding a sweet spot between the diving from the top left down to the right, the heat loss of the house, versus the heat pump capacity of that equipment. And there's kind of that idea of cold climate heat pumps extending down to much lower temperatures, the opportunity for that heating capacity. And that does leave us start to think about an opportunity for some ductless systems. Maybe you just don't go fully ducted anymore. You go to ductless systems, and now that would give you the zoning that you need, that east-facing glass in the morning, the west-facing glass in the summer. I get my zoning based on that. So there are some great new options associated with high-performance houses. But I just wanted to make sure that you're also familiar with the idea of hybrid or dual fuel options. So what if I wanted to keep my gas furnace and still run a heat pump part of the time? And the answer is absolutely we can do this. If you look at kind of a traditional gas furnace, you'll notice on top of the furnace is an evaporator coil. Looks like what it normally looks like. Looks like an air conditioning coil. Underneath it is the natural gas burner. The only issue with this is the heat pump can't run when the burner's on, because if I have the gas burner on, the heat pump is seeing air that's already too warm. So I can't run them simultaneously. What it means in this system is I need a control to switch between the gas furnace and the heat pump. And that's based on the efficiency of the heat pump, the outside temperature, and maybe on the cost of fuel. You can think about time of use rates. So what the industry now has and needs more of is controls to run these systems. There are a couple out there now that will look at the outside temperature, will look at the efficiency of the equipment that you've installed, and will make a decision based on time of use rates. Okay, today, in the evening, it's best for me to run the heat pump. Later tonight, when it gets really cold, or first thing tomorrow when the price of energy goes up, electricity goes up, I'm going to run my gas furnace. Justin, you've seen a couple of these controls. I would say they're in their infancy, but we're starting to see this.
There's several from the heat pump manufacturers, and we're seeing here also cooperation with one of our local utility here, and they're doing exactly what you're describing, Gord. The utility is actually looking at what that switchover is, and based on what the house profile looks like, how old it is, and the type of equipment that's been installed. But I do have one to be delivered here soon. It's a coil and an outdoor unit with a control, and it's one from one of the major heat pump manufacturers. So it's a test unit, but they said it's going to be real time real soon.
Right. The other option would be to say, okay, I still want to do a dual fuel option, say a hot water coil that runs off of a hot water heater. In this case, I'm also showing the possibility of electric resistance coil, but notice where the heat pump or A coil is. It's actually below the heating element. So this is a traditional air handler, heat pump air handler, where the cooling section, the heat pump section, is just above the fan, maybe even on the return side of the fan, but our other heating coil on top. And you say, well, can I do that with a gas furnace? Not at the moment, but I could feed that gas, hot water could be gas based. So my backup heat, my hybrid fuel, in fact, could be hot water based. And in this case, now both coils can operate at the same time. I can run the heat pump coil and I can supplement it with a little bit of electric resistance or a little bit of hot water from a hot water coil. So this is, to my mind, one of the things that you're going to transition to. You're going to start thinking about combination systems where you're using a tankless water heater or a boiler to heat some hot water, and then using that to manage the air temperature coming off of the top of the coil. And you can manage water temperatures, you can mix and match equipment. These kinds of combo systems, I do need to remind you, need to be P911 tested. So we want those combo systems tested such that they work both domestic hot water and heating mode at the same time. So we want tested equipment, certainly in zero energy or low energy houses, we want to use P911 tested equipment. But it does show there's going to be these new equipment options. We can use on the left-hand side a gas furnace with a hybrid heat pump, or on the right-hand side we could use some radiant-based heat pumps, hot water coils with heat pumps on them, or in the middle we could just switch to all heat pumps. So there's lots of new options that are available to us. Here's showing the gas furnace with a heat pump and then a water heater. As part of that, here's showing, for example, an air handler, hot water air handler with a really good efficient hot water heating system, or the ductless mini split. So lots of options. The point is, start including heat pumps somewhere in your heating and cooling system. You need to have heat pumps there. Now, we only have about 10 minutes left, Justin, in terms of before we want to get to some questions. I'll just run a few quick slides on ventilation and then dehumidification, and then we're time for questions. So I just wanted to, everybody knows ventilation here in Canada. You're all putting HRVs or ERVs in your houses. I just want to remind you of a couple of things. First and foremost, ventilation is kind of two elements to it. There's on the right-hand side, I need continuous capacity, but I still need source control. I need to understand the cooking and bathroom odors and so on. I need to have source control on over top of really wet, stinky, high pollutant areas, and then I need continuous capacity. But be mindful of this. I mentioned it earlier. Ventilation really now is the only constant flow in home, especially in low load houses. My zero energy, net zero house, the heating system really hasn't run now. Sorry, the cooling system has been running now over the last couple months, but I won't start heating until about October. The cooling system will turn off. It's going to be the ventilation system that's running all the time, and in which case you might say, should I go to fully ducted systems? Rather than thinking about running large ductwork to every room in the house, why wouldn't we run small volume ductwork? Imagine that getting rid of the bathroom fans, because bathroom fans eliminate extra. If you get rid of the bathroom fans, you eliminate holes in the enclosure. And in fact, there are some new zoning options for ERVs and HRVs that get you a better boost of flow. But I just want you to imagine the benefits of continuous fresh filtered air to the bedrooms. Your heating system isn't running, your cooling system isn't running, your homeowners still want fresh filtered air. Fully ducted HRVs or ERVs may be back on the rise. We used to do them 30, 40 years ago. They may be back on the rise. And I thought I'd show you, this is called a Whispered Posh powered grill, that when you hit a bathroom switch, this grill actually opens up, runs off the ERV. The ERV goes to high speed, and now we end up with more exhaust flow. So if you're worried about the capacity of an HRV vent or ERV vent in a bathroom, you can boost that capacity by going to a zone type system. And I just wanted to show that there's now ERVs and HRVs that have HEPA filters built into them. So if you did run them continuously to bedrooms, you could be offering your clients HEPA filtration. So we know ventilation pretty well. I just want to mention that, remind you that it's the only constant load now, the only fan that's moving all the time, or that needs to be moving all the time. And we may want to do it separately from our heating and cooling system. The other thing is, I'm going to remind you, for those who need the reminder, switch to ERVs. In almost all cases in Canada, across Canada, they do a better job of moisture control in summer. They avoid over drying in winter. They don't need a drain. They're not, as long as it's rated for cold weather. You need to find one that's rated for cold weather. There's dozens of ERVs listed on the HVI website, dozens and dozens, and about half of them are listed for cold weather. So make sure you choose one that's rated for cold weather, but otherwise you're switching to ERVs. I want to mention, Justin, and you'll talk quickly on this one, the need for makeup air. You might be interested to know, Justin, we have a new, or at least a revised standard called the F300 depressurization standard, which is going to provide a guideline for intermittent exhaust appliances. The house should not go more than minus 25 Pascal negative. You will know what that's about. It's really the capacity of those fans. The range hood doesn't work very well when the pressure's too high. And you see this with bath fans and other equipment as well.
Yeah, we see it with lots of things. I mean, in particular, I'll give an example, Gord. We had a house that was built to almost passive house. Well, it was passive house. It was 0.53 ACH 50, and they put the big range hood in it. So we just wanted to see what would happen, for example. So we actually took the makeup air system and got rid of it. We closed it off on the outside and taped it shut. Turned the range hood on, and we brought the house to minus 60. But the flow was only it was rated for maybe 1,400, and I think the flow was well under 300 at that point. The house is very tight. Small house.
Very tight. And the fan can't move air against that pressure, so the fan capacity goes down, which is not fair to a homeowner. It's not safe, quite frankly, on a gas range. We want to make sure we still have that flow. And so this is a controlled hole. Get used to it. There's a sensor that's built into the range hood vent, and you hook it to this makeup air and you go, where does the hole go? Pretty much anywhere in the house, put it in the mechanical room. It's only open for a short period of time when the range hood is operating. Doesn't necessarily need to be heated. Somebody's going to say in northern Alberta it needs to be heated. It may be if it's on for long periods of time, but in general.
And Gord, there's some wonderful options if you want to do the Rolls-Royce model. There are some very well engineered systems that are fan powered, that are connected to that hole to the outside with dampers, with MERV 13 filters, with variable stage reheaters on them that'll, if you size it right, pretty much bring the air back up to 23C, 22C or so coming back into the building. But you're going to need, 20, 40, 60 amp, depending on what you're bringing in on the electric service, because that's what it runs, is electric resistance heaters.
Right. And so thank you for that. And I wanted to do just a little bit on indoor moisture, and I'll just remind folks that this is called the Sterling chart. It's been around since 1973, that says the healthy range to live in is 40 to 60%. I'm going to key in on Justin just on summer issues. So we'd like to stay below 60, 50 to 60 is kind of where we want to go. And I just want to remind folks that the 4 ways to control moisture in humid weather. 1, create tighter houses. In humid weather, we don't want uncontrolled, willy-nilly airflow of hot, humid air coming into a house. So the tighter you make your houses, the better it is from a moisture control. 2, use ERVs rather than HRVs to ventilate. They cut roughly in half the amount of moisture that would otherwise come in by ventilation. Third, use a properly sized air conditioner. But as Justin alluded to, the problem with the air conditioner is it's not running as often because we have low load houses, and our latent loads are on the way up. More people, more time indoors. And so the air conditioners aren't as well designed or as well suited to remove the moisture. And fourth, and I just want to put it on your list of things to think about, is whole house dehumidification. And I'll go to commissioning that air conditioner for dehumidification. I'll remind you that the air temperature off the coil needs to be 2 to 3 degrees Celsius below the desired dew point. And the dew point of comfortable air, 23 Celsius, 50% RH, is roughly 12 degrees Celsius. So if you turn on your air conditioner and you run it for 6 to 8 minutes, you should measure the temperature either at the first run or off the top of the coil, somewhere between 9 and 10 degrees Celsius. And Justin, if it's not there, they basically have 3 choices. You can help me with those.
Yeah, you have it listed here. I mean, one is adjusting those fan speeds, and it might be in concert with the refrigerant levels. So whatever desired, superheat, subcooling levels that you're looking for. But that can be messed around with, to your point of the increasing run times, is that fan speed adjustment. Again, assuming your refrigerant is done properly, and I'll give you an example of most Canadian group here. I'm in Denver, it's like Calgary. We don't have opportunity for much latent load at all ever in the buildings. A 42 RH in summer runtime is amazing. Usually it's around 35 or 6. It's probably like Calgary, right? So we steal a little bit of that capacity, of the latent capacity. We steal it back and we increase the fan speed a little bit higher. We clock maybe 8, 10, 12% faster than that sort of 400 cubic feet per ton rule. So maybe like 450, 440 per ton. Now, if I'm in Minneapolis, Toronto, Nashville, I might slow that fan down, to your point, Gord, and I'm going to slow it down to maybe 360, 350 per ton. And what I'm trying to do, to your effect here, is drop it to 8.75, 8.5, or 9C, right off the top of that coil. Because when that air is colder, I don't want to freeze the coil, but as I slow that air down, give it some hang time across the colder coil, I get increased dehumidification.
So just a little thing to think about, and ultimately you may want to start thinking about whole house dehumidification in the spring, summer, and fall. Certainly in basements, there are now some great options to keep that moisture level in a much more balanced range. I won't do that one. And then just a few quick slides to finish up. That I want to encourage testing for performance of HVAC systems, and it's 4 things that you're going to measure: duct pressures, kind of the blood pressure of the system; airflow at the air handlers; airflow at diffusers; and refrigerant checks. And it's a simple gauge that you're going to measure. What was the design pressure? Remember, we said it used to be designed at 0.5. Now they're designed maybe at 0.6, 0.8. Measure the pressure. If and when you get a comfort complaint, first thing you do is take the blood pressure of the system, the duct pressure. Is the duct system designed correctly? And second, you would measure the flow at the furnace. There on the left, it's a drop-in little piece that drops into the filter slot, and it can measure the flow. Is the system moving the right amount of air? Then you would measure the flow at individual registers. Was I getting that 33 CFM that I needed, or the 66 CFM that I needed out of that room when the system is operating? And lastly, and Justin, you'll speak to it really quickly because we got to finish up, but it is important to do refrigeration checks. Most contractors here, they basically use default settings, and because we're building throughout the year, they don't necessarily do the checks in summer and winter. Could you just chat about that?
It's real critical. I mean, your system design can be well off, but here's the good news of this, to be quick. There are several different systems that you can plug in all the variables. For example, model number, outdoor unit, indoor unit, coil type, line set length, and diameter. You can put gauges on, and then it can give you a real-time feedback report. There's 2 or 3 systems on the market now, the various costs. But I'll tell you, even recently, just as our contractor was out, he's had a general contractor's value oriented type gauge. It wasn't a lot of money, and it was literally showing me the parameters based on the system that I was looking for. So superheat, subcool. So lots of advances as far as the digital equipment and the gauges that the contractors can have. And I know they most have their favorites and so forth, but it's critical to get this right.
Thank you. And so based on that, Stacy, let's go to any questions.
We have one that got put in the chat about 145, which was from Fauzi asking the temp rise, the 25°F and 45°F and 55. Is that a temperature rise?
That's a temperature rise, yes. Well, the 25 was the temperature fall in cooling mode. So if the air came in at 75, it would come off the top of the coil at 50 degrees. But yes, that's temperature rise, temperature fall that you would expect off a typical furnace, typical air conditioner. Good question.
Okay. And then we had, why don't you consider roof attic heat gain, such as asphalt, steel, slate, and impact to cooling loads?
It is interesting, Justin. You know this one fairly well. The reason we don't include, but I'll ask Justin to comment on it quickly, is we're well insulated in the attic. So yes, the temperature differential is higher, but there's a lot of insulation, so it doesn't make that much difference. And 2, the cooling load's done sort of average over the course of the day, and we imagine that at night the attic is cooling off. So we're not looking at the instantaneous load, hourly load. We're just looking at average. But Justin, you know this well. It doesn't really account for it.
Yeah, in an unconditioned attic, so if we're saying insulation's on the ceiling or the floor, and we've got some soffit and roof vent situation going on, the software here is using some by climate assumed hourly attic temperature in that calculation. So it is assuming some hotter on a summer day, colder on a winter day. But it's sort of a gray area. Where it falls apart a little bit is when because I saw a question on here, when it's a compact or conditioned roof assembly and the insulation line's now under the deck, and there are inputs, by the way, for roof color, just to be clear, because I saw that comment. That one, we're not quite there. That one's a wild one because by climate, and I'll say we had this occur where people are spraying R20 or using R20, some insulation type on the bottom of a roof deck in Phoenix, Arizona. Well, the software was thinking it was that attic temperature I was talking about, not the temperature that the sun was shining on the roof deck and how hot that was. But I think we're going to get there with some adjustments to software and so forth, because we are building so many different assemblies now.
So that is your biggest risk, guys, is the cathedral, because it's not taking into account the temperature of the shingles. It's saying, well, I'll use Fahrenheit because Justin was using Fahrenheit. It's 90 degrees Fahrenheit outside, so that's my temperature difference, 90 to 75. But in fact, if the shingle temperature is 140 degrees, the design should really be done at 140. And so yes, you're at risk specifically in cathedral applications. You'll notice in attic applications, even if you change the temperature, it doesn't have that much effect because it's R60 typically. But it's a really good question, and one that they're quite astute to understand, and we've noticed as well. Good one. Other questions?
Yeah, I think Grant was just following up with that, saying that the angled and flat roofs, typically darker ones, are a major heat sink, and you listed walls on solar heat gain.
Attaboy. Yes, very important. Absolutely. Certainly understand. Yep.
And then Zoran wants to know, window to wall area. Should we keep designing houses over 17% in Canada? If it is a case, code requires windows with better, lower U value, but is it reasonable taking house as a system?
Well, obviously, it's hard for me. I ask all the time. We asked it last week. Justin, there was 2 or 3 architects. Are we going back to smaller windows anytime soon? We're like, no.
Yeah.
Apparently, we're all exhibitionists. We all want people to see everything that we're doing. I find that interesting. But it doesn't seem like we're going back to smaller windows, which means we have a couple of choices. much better glass, uh, exterior shading, right? Because it's really a cooling issue.
Hmm.
I mean, there's a winter comfort, and interior shading doesn't help us that much because the shades still get warm, and you still have that gain coming off of there. So we'd have to look at exterior shading. I don't, Justin, do you have any thoughts? I don't see us going back
Yeah,
to.
yeah, and I've seen concept windows where they've got integrated exterior shading and that, but I just don't see it. I mean, I know we all want to fight it as there's sort of this purest of energy, and we know that it's the big hole in the building, and triples are expensive and quads are really expensive, you know. Um, I they just love designing windows, flat roofs and windows. You gotta, you know, if I want to pick on something, Gord, be critical today. Flat roofs and lots of windows. I don't know. I don't see it going away. Not today.
Not today. So here's the answer I would give is this. You would say to a homeowner who wants that much glass, fair enough. But you need to understand we're still doing we're going to go to triples, we're going to go to double low E coatings. That's a little more expensive. And we're going to change your heating and cooling system. We aren't going to do the traditional forced air because I'm going to need zoned systems. I'm going to have to understand that east facing window facing the lake in the morning, that's going to be a problem, and you're not going to be comfortable having your bowl of cereal there in the morning. I'm going to need a cooling system for that room alone. That west facing, where you're, in this case, maybe it's the sun shining and it's west face, and that's where you like to have your dinner parties. I'm going to need a separate cooling system there. So it is going to change. Windows alone could change your decision as to what kind of HVAC
Yeah.
system you're going to install.
Yeah,
And
and and that's a big zonal problem, Gord, right? So, you know, is it going to be driven through one single air handler with multiple zones, which is, I got to say, is really hard. It can be done, but it just adds a lot of complexity
right.
for balancing purposes. And would we rather than, and I'll throw sort of one of my friends up there, would we rather just run a refrigerant line with a control wire in it for an individual zone system, or ductwork?
Right.
What's easier to get there? You know, a bundle that's an inch and a half in diameter with the insulation, or, you know, a supply return and all the other things.
Yeah, and so that variable refrigerant, our good friend Paul Magleby, big custom houses in the mountains in Utah, he's been doing variable refrigerant now for what, 10 years at least,
Mhm.
based on cooling loads alone. Everybody wants a view of the mountains, which is typically west, and he's, boy, rather than running forced air ductwork and zone dampers and so on, he's just said, yeah, we're just going to go to variable refrigerant. And they're using a series of air handlers in this location, a mini split, a cassette over here. I see that as, but they have to be done correctly because it's a whole nother level of expertise, and you don't want to chintz out on the quality because you need commercial grade equipment to do that kind of work.
Yeah, and it's the concealed fan coils or air handlers that are, you know, in a mechanical closet. I get the pushback all the time at the wall thing, and, you know, now they're sealing cassettes as well. Many different configurations that you showed on one of the slides, Gord. So, um, you know, I don't know. I'd rather look at that thing up here that's behind me somewhere up there on the wall than not be able to sleep at night. So I don't know, right? So there's one of them. One of them back here in our test house. I think it's right there. There it is. I'd rather look at that than not be able to sleep at night because my bedroom's 80 degrees.
Fair enough. Sorry, just go back. I'm not sure what happened here.
Oh, sorry, Gord. I was putting up the end slide there because our address has changed there.
Oh, fair enough. Thank you.
So I can switch it back if you need to go in there.
No, that's fine. Any other questions?
Yes, we have quite a bit more here to go. Patrick asked, do you have any recommendations for sizing heat pumps for heating? Code only asks for satisfying the design heating load, but heat pumps are at a disadvantage. You've got the lower the temperature, the lower the heating capacity.
Sure. So when you're sizing a heat, it depends on whether you're using dual fuel or not, or trying to have the heat pump. How far do you want the heat pump to go? See, I'm a big believer in that sizing guideline of size the heat pump to the cooling to the cooling load, and maybe 25% more than cooling load. If that achieves your heating load, then that's fine. But you do have to look at the rating point. If you're in Edmonton, you got to find a heat pump and match the capacity. If it can only get me down to -15, then I got to have additional backup. So use the heat pump, size the heat pump as far down as you can go without oversizing on the air conditioning side. A pretty good rule of thumb is say 25% over the cooling load, and then use backup heat. I'll call
Yep.
it dual fuel or hybrid after that.
I agree with that, Gord. That's the perfect opportunity for pushing some hot water, whether it's through a heat pump, water heater, boiler, or something. If you want to do a fuel approach, take the basement offline because it doesn't have a cooling load anyways, and just
Right.
call it your heating load. Just one idea.
Yep. Thank you.
Okay, Bridget asks, how do you address comfort issues through the HVAC systems after a build once complaints start coming in?
Yeah, so this, of course, is a big part of my world. And, as the engineer, the first thing I do is I do those 4 measurements that I spoke of: pressures, temperatures, blood pressure, I'll call it duct pressure, airflow, and at the individual runs, and temperatures of the individual runs. Let's at least see if the HVAC system's doing what it's supposed to be doing, and then look at, can we balance it up? 9 times out of 10, duct leakage is a problem. Now, maybe it's 7 times out of 10 duct leakage is a problem. So I recommend fix that duct leakage. Second, then we start balancing, moving this. And the balancing is always this: where's the thermostat? The thermostat is sitting in a nice, warm, toasty spot, sort of nestled between the kitchen and the family room. It's seeing nice, warm, toasty, kids running around all the time, and yet the master bedroom or the room over the garage is getting cold. So do I need a different temperature sensor in a different location, sort of a poor man's zoning, or do I simply turn off all the registers near the thermostat, in other words, to increase run times? I say this all the time: you want to make your bedroom warmer, make your living room colder, right? And well, I don't want it colder. No, it's still going to run at 21 degrees if we're talking a winter issue. So that's what I would look at. The second would be the cooling load, is to understand if it's a room that's too hot. Here's a really nice, we've talked about this one before, I think, in sessions. Jim Larson from Cardinal Glass, their work would say, if you have more than 15%, get this one now, window to room area. So if you have a 100 square foot room, a 10 by 10 room, and you have more than 15 square feet of glass, that's a good candidate for discomfort if it's facing south or west. So big glass, small room, you're going to have comfort issues. How do I solve that? It's basically exterior shading or blinds to say it's a cooling problem, unless I'm prepared to put in zoning. So it's measurements, number one, compare those to the designs, and then it's adjustments of duct leakage and adjustments of balancing to get longer run times and more airflow to other rooms. Justin, any thoughts?
I'm following 100% with you, Gordon, for sure on when you get to a house and measuring those critical components as well. And then just really taking an observation is kind of what you're stating is, what are the conditions that you're finding? And also, I think, to reinforce, now you've got occupants in the building, and so there's a good bit of listening that goes on as to how they live in the house and what they really feel or expect, right?
Right. And I'll put it this way. I do Terry on investigations. 80% of the ones I go to, I say to homeowners, so what's been done? Some guy came, he changed this damper. I said, did they measure anything? Are there any results? I asked the warranty rep, are there any measurement results? 80% of the time, nobody's done any measurements. And I'll find that the fan speed was not set up correctly. It was just set at the default speed. And the pressures in the ductwork system were designed at 0.15, and they're at 0.05. They're at 1/3 the pressure they're supposed to be, which means the air never gets to the room over the garage. I got to increase that pressure, which means increase the fan speed, get rid of some of the duct leakage, turn down some of the dampers to encourage air to get to that back end. Measurements, and maybe it's the engineer in me, but I would say measurements first before you tell people everything's working fine. True measurements. And it's not that easy to get accurate measurements of airflow. You need to invest in some equipment. It's not a little wave of magic wand. You need a proper.
But it's not expensive for anybody to have a simple manometer and go and take an overall total external static pressure measurement, and get a reasonable idea of what's going on. The one that we've had, how many builders they call us and we're like, could you just go buy a small thermostat, sensor, and stuff it in above the coil and just give me a number, right? Give me a number for cooling.
Exactly. Good.
Okay.
Almost at time, but anything else?
Well, if you don't mind, do you have time to stick around?
I could stay on for a minute or two, yeah.
Yeah, because these are really good questions that are coming through, and I think that everyone on the line would find value in the answers to these. So Armando asks, is it more effective to blow air across the room than to drop it above the windows and doors?
Well, I would say that's a decision of cost and location and architectural. You can do either one. if it's easy to get the duct out to the perimeter and drop it over top, that's fine. But if it's difficult to get it there, why wouldn't we blow it across? If it shortens the duct run and so on. So I wouldn't say it's good or bad. I
But
would say
Gord,
take your pick.
don't blow air on people. So you
No,
have to
don't blow
think
air on
about how
people.
the
Fair enough.
rooms, the function of the room, and how the room's used. And I'll throw. That's good to hear from Armando too. There may be some in the analysis to your glazing perspective, Gord, of 15 per 100, 15 and 100 square foot room and so forth. There may be some instances where you just have to do it. You have to put it to the perimeter, and because you've got so much glass there, or some door that's just thermally not adequate, right?
Right. Thank you.
Okay. Is the noise, the dB, an issue with high velocity, small duct diameter systems?
Sure can be, and the codes have some guidance on this, not codes. There are no codes and standards that actually give us a noise in residential code. What they give us is a velocity coming out of the registers. It's somewhere between 8 and 1,000 feet per minute. So when I go out and do warranty claims, if it's over 1,000 feet per minute, it inevitably sounds noisy, and I say the guidelines would say it's under 1,000, unless you're doing something special, or unless you got an acoustics engineer. It doesn't have to be noisy. There are duct silencers and so on, but it comes down to too high a velocity, too high a noise.
Okay. David asks, how about operating windows, cross ventilation through rooms using stack effect ventilation chimneys, solar chimney for passive zero energy ventilation?
Sure, I'm totally good with that. I remember a customer called me and he said, I understand you're the guy, but I look online and you're an HRV guy and you're going to want me to put an HRV in my house. I don't want an HRV in my house. I said, sir, just tell me what you're up to. I'm up on a hill. I have these passive solar windows, vents, and so on that, and I just want to ventilate naturally. And I was able, as an engineer, to go to the house, recognize what he was trying to do, understood how he would design the house for passive ventilation, was able to write a letter saying, this gentleman, the house is adequately ventilated. This is years ago, but adequately ventilated without the need of mechanical ventilation. You could do it. It's not that easy, because I said to him, sir, you need to understand, some of these windows are going to be open in the dead of winter. He goes, yeah, I understand that. I like wearing sweaters. I'm okay with that. I've got them calibrated. I'm only going to open them an inch. We just need to understand you can do that. And I said, you're not going to get any moisture control in the summertime. I'm good with that. I don't have air conditioning. I'm not going to run an air conditioner. I'm shaded. I don't care about the moisture, the humidity level. Fair enough. So if you're not worried about relative humidity and you're not worried about temperatures, cold or too hot, then you can passively ventilate. And could you passively ventilate some days? Absolutely. Today is a beautiful day. Open your windows. But you still, in most houses, need the capacity for mechanical ventilation. For the next homeowner is going to say, I'm not opening my window. I need to ventilate. If I'm not going to open windows, I need mechanical ventilation. The code goes the other way and says, because people aren't going to open windows, we have to provide the capacity for mechanical ventilation. Could be as simple as a bath fan, but I have to provide the capacity.
Okay, so he follows up with, do you have experience, I'm not sure the pronunciation, Minotaur?
Minotaur, yeah.
Minotaur, combined HVAC all-in-one unit, no external condenser, and Canadian made.
Sure. It's a heat pump ventilator, which provides some extra heating capacity. It's going to have to be a really low load house, because I think it gets you about 6,000 to 8,000, maybe 10,000 BTUs of heating. Not too many houses can be as low as 10,000 BTUs. So maybe you need some supplemental heat. So it's a ventilation system that recovers the energy through a heat pump process. We've already extolled the virtues of heat pumps. That's a great idea. But when it says you don't need to put in a heating system, well, you need to know what is the heat load of your house. If the heat load of your house is 20,000 BTUs and the Minotaur is only giving you 6 of it, somewhere I need to make up that other 24,000 BTUs or whatever the difference was.
Okay,
they're pretty slick though, Gord. There's several.
Pretty slick.
There's several. They're pretty slick, and but it is about the load, and how you place it, and how you're going to install it, and where you're going to install it. And there are then outdoor air connections you have to make though through wall penetrations.
Right.
There are several from Europe that are available here in North America as well.
it must be the up and coming product, because Stephen had followed up and you answered his question already about that product. So that's great. And then Adam asked, what is your opinion on using a whole home dehumidifier paired with an air conditioner size for the sensible load only?
I'll let Justin answer that one. In general, there's nothing wrong with using a dehumidifier to reduce your cooling load a little bit. But Justin, your thoughts?
Well, I mean, I think was it sensible or latent that we're switched there, but you know, it's a good combination. It really is going to depend, I think, on climate zone as well. You will find some, which is pretty unique. There's a few manufacturers, I'll say, that Santa Fe, their SD12. I was really enamored by it. I haven't tried it yet, but here's kind of in that theory. It could be connected to and complement a typical air conditioner, but it has a very small outdoor compressor. So the compressor is brought outdoors, and there's a short refrigerant line connection, hopefully short, but it's a dehumidifier around 120 pint capacity. So that's pretty high. It's variable speed, and it delivers a third of the ton of sensible back to the building. So you don't have the heat discharge. Kind of an interesting theory. And if it's a really low load home, you're getting some sensible cooling and a whole bunch of dehumidification out of one unit. And we're starting to see some equipment come like that now.
And then I can now see the chat or the Q&A, so maybe I'll answer Rob's question. Under the NBC house that has an ERV, how do I ensure, sorry, I missed that one. What is the maximum CFM kitchen exhaust that can be installed before you have to look at install makeup air? The question really is this: you can do a design calculation before the house is built. You assume a certain level of air tightness. It's a calculation based on the square footage of the house, volume, and so on. So I can't give you an answer now. What I can say is there's a simple design tool to that. What you'll find is when you design beforehand, it's ultra conservative, but it has to be. Really what you do is get the blower door test, and the blower door test will tell you exactly what airflow it takes to get above 25 Pascal or below 25 Pascals. So the blower door, you get your energy advisor to tell you what CFM makes the house go more than 25 Pascal negative. You check that against your range hood, and if the range hood's bigger than that, you're going to need makeup air. The next question was, most ERVs require Fuzzy, I guess, or Fauzi is saying most ERVs require drain pipe. My experience is about half of them require drain pipe, but that's fine. I have no problem with that. How do we ensure the HVAC contractor confirms the ducts are properly sized, properly done when a ducted gas furnace to a ducted heat pump? It's typically same measurement that Justin talked about, static pressure measurement. Static pressure measurement, what was the duct system capable of, typically 0.15 in the supply, and I check it against the gas furnace, against the airflow. We can get that done. Then Grant's asking, in terms of comfort, any studies of virtual window impact on occupant comfort? And the answer is yes. Go to Cardinal Glass. They have a comfort calculator, if you will, that nice little graphic. It's not perfect, but it's a really good start. So Cardinal Glass, go there and you'll find that. And then Robbie Schwartz is asking, does manual J, S, or D work for these low-load houses? Robbie, you'll know better than I. Justin, your thoughts? They do have a low-load calculator.
Yeah, there's manual LLH for low-load homes now.
Yep.
But then Robbie's other side is they want to use some other type of heating system or ducting system. And that's going to be this, if that's your goal, I'm going to say then it is a design element, but it can be designed, whether it's small ducts or a combination of different heating systems scored. There's a lot of options. We just had several of these, that came up with a Minotaur. Was that the one?
Yeah. From
Canada, which is a concealed unit. There's a lot of these options, but once we get to the load, we get to the load. And again, though, I'm going to say the windows are going to drive the bus, as you all know, especially when you're super insulating walls. An R30 or R40 wall, and then you put an R5 window in the mix.
It's windows drive the bus, absolutely. And then Trent is asking about other rules of thumb. I said return, high wall, low wall, it's not really there. I would say one of the things that's getting us is that the filter aisles at the big box stores are all, and everybody wants to buy them, have much higher static pressure resistance than what we're designed for. It doesn't make them bad filters, doesn't mean it's going to affect flow. It means that designers are going to have to start allowing for higher static pressure filters because homeowners are just going to go ahead and buy them anyway. So we're going to have to allow for more. So the rules of thumb, it's not fair to say to a client, that filter's no good. They just spent $40 on it. Either you need to supply them with a low static filter, so it's, rather than the big box supplying it, or you need to provide higher static in the design has to provide higher static pressure. Then the supplementary question was, where supplies go, and Armando kind of asked it. Supply, high wall, low wall, it really depends on your duct system, what you're trying to achieve, windows and so on. Typically for cooling, you like it high wall. Heating has always been a low wall. We know we can do heating high wall very easily. We can do heating high wall as long as we've got the right throw of air across the room.
Yeah, so it's going to come down to register selection quite a bit, Gord, and capability. And so that's out of manual T, or you can get really good information when you're doing some tests. If for example, I heard you mention the 1,000 feet per minute. That's where you start getting supply air noise, but it's also going to be a register selection component as well, whether it's an airfoil blade or a stamped steel blade, plastic, something like that. So many different options out there.
And then last question looks like it's, is it better to have 2 heat pumps for a large house? And the answer is, you've already said it depends on the loads. As Justin mentioned, basements basically need no air conditioning. Upstairs needs lots of air conditioning, kitchens don't need much heating. So I would say it's not a question of the size of the house, it's a question of the nature of the loads of the house that determines whether you want 2 systems or not. More and more, I'm going to say we got to look at zoning.
And that the thing about the zoning, maybe we didn't really cover that, Gord, but here's one. For example, we've got another heat pump that's going to show up here, cold climate heat pump. It has 3 out. It has 3, so it's a twin fan. It's small, skinny, goes right against the wall. It can go within 6 inches of the exterior wall. But it has 3 ports to it, so I can connect. In this particular instance, I'm going to put a cassette unit that's a concealed cassette, a wall unit, and then a typical air handler, all on the same outdoor unit. So that's it's kind of 2 heat pumps in one, but I'm connecting 3 devices to it.
Right. Yeah, I love that. Well, great. Stacy, anything else that we needed to cover? First of all, let me say, Justin, thanks very much for sitting in. I will just encourage people to get the CI Live, and thanks for the generous offer of taking Canadian money on par. We appreciate that. And you guys will love the experience if you go down. Obviously, I enjoyed teaching there as well. But thanks very much, Justin. I know we had an incredibly busy
Thank you.
day.
Thanks everybody for letting me in. I see that there's 85, now 69 people. Yeah. It's just great to connect. Of course, that was great to see you. So I won't get to see you for a few weeks down here. So it's always a pleasure.
Thank you. And our thanks to Enbridge for being so accommodating and so generous to the industry to allow these to happen. We really appreciate that. Stacy, thanks for your help. Anything else, final comments you wanted to make?
Yeah, we're just letting everyone know that this is being recorded. So all of the Q&A will be a part of that, and a resource email goes out with that, and any links that we put in the chat will be a part of that resource email. So they'll be able to go and check out all of Justin's stuff on his actual website, which is awesome.
Thank you.
Thank you so much.
Thanks, everybody.
Thanks, everybody.